So this is section 2.3. This is section 2.3. Now we get to learn the algebraic rules of calculating limits. Now we can just stop guessing. Now we can stop investigating. Now we can stop estimating. Now we can actually use laws to calculate limits. Okay? This is going to be a lot more concrete. This is going to be a lot more finite rather than abstract. Where yet the past couple sections have been more like, okay, let's think about the idea of a limit. Now it's like, okay, how do we calculate a limit? How do we actually run the numbers? How do we do that? Okay. So, calculating limits using limit laws. First thing that we have to talk about is that if you can find the limit, okay, if we can find the limit, maybe graphically, maybe algebraically, whatever it may be, you can use these algebraic rules to calculate more limits. For example, if you know that the limit exists at f of x and g of x at a, look, as x approaches a, so maybe like as x approaches 1 of f of x. If it exists at 1 and at 1 here, we know these properties are true. If you can calculate the limit of f of x and the limit of g of x, and you add those two functions together, it's also equal to the sum of the limits as well. Okay? So maybe you can have a polynomial. Like, think about this. If I had maybe f of x was like 2x squared and g of x was 3x, and I wanted to find the limit of that whole thing as x approaches something, right? I don't know, whatever. Then I can actually split it up and take, okay, if I want to do that, I can take the limit of this and then take the limit of that separately, if that might help me. Okay? So if I want to take the limit of a sum, I can take the sum of the two limits separately. Same thing is true for difference. If I change this to a subtraction sign, and I wanted to find, that's right now. If I wanted to take the limit of the difference of these two things, well, then I could separately take the limits of both of them. I could take the limit of this and then the limit of that, and then subtract the two once I get it out in the end. That computes like that. Same thing is true is if I multiply by a constant. That c is a constant. So if I take something like this, let me get rid of this. If I take something like this, if this was like 2 times 3x squared plus 4x, right? If I wanted to take the full limit of that, it's really just 2 times the limit of this thing. Okay? I can take the constant, if it's a constant, and remove it outside the limit and multiply it if I would like to. That will be extremely useful a little bit later on when we get more into derivatives. We can bring that number all the way on the outside and then calculate the limit separately, and then in the end, multiply back to that number. Okay? If I take the product of two functions, so maybe I have the limit of two things like x plus 1 and then x plus 3, right? I can take the limit of each one of those and then multiply them together in the end. I could take the limit of x plus 1 and then the limit of x plus 3 and then multiply them in the end if I needed to, if that helps me. And I could also do that with division, with one exception. Like I could take the limit as x approaches a of f of x over g of x, and then take it separately, divide it up and say, okay, I take the limit of the top and then divide it by the limit of the bottom, as long as the limit of the bottom is not 0, okay? As long as the limit as x approaches a of g of x, the denominator one, is not 0. If it was 0, then, all things would go haywire anyway because I'm dividing by 0, okay? All right, so let's calculate some. Use the limit laws in the graph to evaluate the following limits. See, right now, the only way we know how to do a finite limit, like to actually find the finite limit of something, is to look at its graph to find the limit, right? Otherwise, we're just estimating. Otherwise, we're just guessing. Otherwise, we're saying, okay, I think it's going to go to this. So let's look at the graph and do some operations with it. So take a look at what I've got here. This is the limit as x approaches -2, right? Of this sum. Okay. Well, I could rewrite that to say, well, then that's the limit as x approaches -2 of f of x plus the limit as x approaches -2 of 5 times g of x. Whoa. And then I could also simplify it even more. And then I could also take it separately and say the limit as x goes to -2 of f of x plus, now, see how this is a constant right there? I could take that constant and bring it out front. 5 times the limit of g of x as x approaches -2. Okay, do you see what I can do algebraically there? I can manipulate it to kind of make it a little bit simpler. Why is this going to make it simpler? Well, can I take the limit as x approaches -2 of f of x? What is it? Let's find it. As x approaches -2 of f. Look. Does the limit exist? Yeah, they're both going toward the same number. Even though it's discontinued, even though I've removed that point out there, right? It's still, the limit is still going to the same thing. So isn't it going to +1? So that means I can take, that's just +1. The limit as x approaches -2 of f of x is +1. Plus 5 times the limit as x approaches -2 of g of x. Okay, so what's happening as I approach -2? What y value do I have there? -1. You see that? 1 minus 5 is -4. So the full limit as x approaches -2 of f of x plus 5g of x is -4. Make sense? Let's do that again. Let's take the limit as x approaches +1 now of f of x g of x. Well, algebraically, I can say, well, if I've got a product like that, I can take the limit as x goes to 1 of f of x, and then times the limit as x approaches 1 of g of x. Okay, what is the limit as x approaches 1 of f of x? What is the limit as x approaches 1 of f of x? Okay, look here. I'm going na 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 na. Na 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 na. What is it? 2. What is the limit as x approaches 1 of g of x? Na 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 na. Ruh-roh. Do I have a left side limit, but do I have a right side limit that matches that thing? So what do I say about the limit as x approaches 1 of g of x? It does not exist. And if one doesn't exist, the whole limit does not exist. Okay? Because the limit as x approaches 1 can be calculated from the right and the left, but they're different. And if they're different, the full limit does not exist. Now, I could have tweaked this problem very subtly to make this come out to be correct, or to make this come out to be doable. If I had just done that, and then I said, okay, only calculate one side limits, only calculate left side limits of all these things, then I would have been able to do this. Or if I had just done that, okay, only calculate right side limits of all these things, it would have come out to be different. Does that make sense? Take a look here. Last one on this page. The limit as x approaches 2 of f of x divided by g of x. So remember that that's equivalent to saying the limit as x goes to 2, sorry about my weird arrow there, x approaches 2 of f of x divided by the limit as x goes to 2 of g of x. Okay, what is my numerator then? What is the limit as x approaches 2 of f of x? Let's kind of get all those markings out of the way. Okay, well, I'm going closer to 2 on f of x. What do we think? What do you think that's going to be? About 1.4, 1.5, somewhere in there? Let's say 1.5. What about the limit as g approaches 2? You got it. What is the limit as g approaches 2? 0. What do we say about the limit? It does not exist. The limit, full limit, does not exist. Okay? And the reason, because it's divided by 0. Okay? Didn't even matter what I estimated it to be in the numerator, because it turned out to be divided by 0. Questions about that? Okay. Let's take a look here. More rules, more limit laws. If we use the product law repeatedly, we could take a power law. For example, here, the limit as x approaches a of f of x to the nth power, to the second, to the third, to the fourth, to the whatever. As long as n is a positive integer. If it's negative, things go haywire because it goes down to the bottom. If it's irrational, if it's a fraction, it turns into a root, which we'll talk about later on. But as long as n is a positive number, I can take that power and bring it outside the limit. So this is like saying the limit of x squared is really equivalent to the limit of x squared, right? To any power. So if you could calculate the limit separately, if that helps you in any way, you could calculate the limit of just the variable and then raise it to the power, and then it would help. We also have some unique cases. If you have just a constant, like the limit as x approaches 2 of 5, no variable, it's always equal to the constant. Why is that the case? Because it's just a horizontal line when I go to graph. Like think about the equation y is equal to 2. Right? Think about the function 2. Y is equal to 2. All of my x values lead to the exact same y value, right? And they all lead back to that constant. So the limit of a constant is always the constant. The limit as x approaches a of x is a, and that is an extremely powerful statement right there. That's a very powerful statement right there. Okay? This is saying that if you have the limit as x approaches a of just x, all you need to do is just plug in that a for x, and there's your answer. There's your limit. That is going to lead us to the substitution rule, which is right down there, which is really close to us. Okay, that's a very powerful statement right there. The limit as x approaches a of x is equal to a. Okay? Also, and this kind of leads us into the next rule. The limit as x approaches a of x to the nth power is a to the nth power. So this is like saying the limit as x approaches 2 of x squared is 2 squared. More substitution again. The limit as x approaches 3 of x to the third is 3 to the third. Same type of thing here for square roots, nth roots. Doesn't have to just be square. The limit as x approaches a of the nth root of x is the nth root of a. I can just plug that in and solve. So the limit as x approaches 3 of the square root of x is the square root of 3. Okay, also, that works for any function inside there as well. Okay, you can also take the limit and bring it inside if that helps you, if that assists you in any way. Okay, I always have people saying like, "Hey, is this available online?" Because some people like to print off all these things that like have all the rules and stuff all that on them. By all means, all of these theorems and equations that we will use in class are always on the document online. So you feel free to print whatever you need to. All right, so let's evaluate. Okay, I'm going to take it a little slow for right now, and I'm going to take it a little bit more thoroughly than what we would usually do. And I'll show you here in a second why. We kind of have to appreciate the substitution rule because we're going to have to do it the long way, not really necessarily long way here, more algebraic way. Here's what I mean. Do you see how I have a trinomial on the inside there? That means that I could take that limit and say, okay, I want the limit as x approaches 5 of 2x squared minus the limit as x approaches 5 of 3x plus the limit as x approaches 5 of 4. Oh, sorry, as x approaches 5 of 4. Right? I can basically distribute the limit in. Then bring out this 2. 2 times the limit as x approaches 5 of x squared minus 3 times the limit as x approaches 5 of x plus the limit as x approaches 5 of 4. Didn't change that one. I just took all those coefficients out. Now we can do that whole substitution thing. 2 times 5 squared minus 3 times 5 plus, now, what is the limit as x approaches 5 of 4? Is it 4 just a constant? Is there any x value to plug in? There's no x value to plug in. This is a very common mistake. People always try to tell me that that's 0 because they're like, oh, there's nowhere to plug it in. Not true. You have to remember the limit of a constant is the constant itself. 4. Okay? Watch out for that. That was a huge mistake people kept making last year. The limit of the constant is the constant, not 0. So this is 2 times 5 squared, or 50, minus 15 plus 4. So 50 minus 15 is 35, plus 4, 39. This is going to lead us to direct substitution because look, did I need to do all that work? No. What would I get if I plugged in 5? 50 minus 15 plus 4. The exact same step as we get right there, right? So while it's good to know why this works, in the end, I'm going to expect you to go from here to here. Okay? That's what I'm going to expect. Let's take a look and do the same thing for part B and really justify why those steps are true. Exactly the same as we did with our first one here. Okay, so the limit can be broken up numerator to denominator as long as the limit of the denominator is not 0. If I take the limit of the bottom and I plug that in, does it come out to be 0? No, so we're good. Okay, so we can take the limit of the numerator. Again, we're kind of crawling before we can walk here. Of x to the third plus 2x squared minus 1 divided by the limit of the denominator of 5 minus 3x. That whole thing. Right? Now we can distribute in the limit. We can say the limit of x approaches negative 2 of x to the third plus, and now I'll do 2 steps at once. Since it's 2x squared, I'm going to take that constant, bring it out, 2 times the limit as x approaches negative 2 of x squared minus the limit as x approaches negative 2 of 1. All divided by the limit as x goes to negative 2 of 5 minus the limit, minus 3 times the limit, as x approaches negative 2 of x. Okay? So I can bring it all in. I can bring that limit to everything, basically. So now we evaluate. We say, okay, the limit as x approaches negative 2 of x to the third is negative 2 to the third, plus 2 times the limit as x goes to negative 2 of x squared, which is 2 times negative 2 squared. What's the limit here? The limit as x goes to negative 2 of 1. 1, right? Not 0, not negative 2. It's 1. It always goes to the constant. All divided by, excuse me, the constant, again, same thing here. The limit as x approaches negative 2 of 5 is 5 minus 3 times the limit as x approaches negative 2 of x, which is just negative 2. And essentially, look at that step comparatively to the very beginning. All I'm doing is plugging in negative 2. That's all I really did. So negative 8, that's positive 4, positive 8, minus 1. Oh, I love it. Sorry. You're the only one that come back to me. All the people that say we're going to come back to work here, you're the only one. Appreciate it. Sorry about that. And we're back. And then we plug in 5 minus 3 times negative 2. So 5 plus 6, right? Those will cancel. Negative 1, 11. That make sense? Negative 1, 11. 39. Yep. Now, all sum total of all of this stuff, basically just to say this directs the substitution rule. Okay? If f is a polynomial or rational function, and we got to have a polynomial or rational. When f is a polynomial or rational function and a is in the domain of f, meaning as long as a is defined, then the limit as x approaches a of f of x is just f of a. All you have to do is plug in that value. Functions with the direct substitution property are called continuous at that value. There is a whole section 2.5 that we will talk about continuity. Functions with the direct substitution property are called continuous at that value, and we'll be studying section 2.5. However, not all limits can be evaluated by direct substitution as follows. We had this example before. Do you remember it? X squared minus 1 over x minus 1. Maybe it was plus on this. But we had something very similar to it, I guess, if we did not have that exact one. Okay, if I've got the limit as x approaches 1 of x squared minus 1 over x minus 1, can I do direct substitution as it sits right there? As it sits right there, can I do direct substitution? If I tried to, I would do this. And I would not be able to, right? But is there something that I could do to reduce that function? I could factor it. That's what you meant, Mac?
Yeah.
Right. So we could take the limit as x goes to 1 of x minus 1, x plus 1 over x minus 1. Presto changeo. The limit as x goes to 1 of x plus 1. X plus 1 is an equivalent function to x squared minus 1 over x minus 1. Now, can I do direct substitution?
Yes.
Yes. So it's 1 plus 1 or 2. So the limit of that function is 2. Okay? So sometimes, even though it may not initially look like we can do direct substitution, maybe there's something algebraic we can do with it to reduce it down somehow so that you can do direct substitution. Note in example 3, we were able to compute the limit because it was equivalent. Those functions were equivalent. Key thing to point out here, even though, and this is another case where I'm saying the same thing over again, even though the function was not defined at that value, the limit still existed. Okay? The limit still existed. If f of x is equal to g of x, and this was our x squared minus 1 over x minus 1, and this was reduced down to x plus 1. When x is not a, then the limit as x approaches a of f of x is equal to the limit as x approaches a of g of x, provided that the limit actually exists. Okay? The limits are equal to one another as long as they exist. All right. So let's take a look here then. Yes, question.
What happens if you can't get a limit where it's not, like, do it algebraically to get it solvable? Like, what happens if it's still, like,
With that,
something divided by 0?
right, that's what we'll have to talk about, like, for the rest of the like, what else can we do to find limits? What else? And what does that imply if we cannot find the limit?
Okay.
You know what I mean?
Yeah.
If the limit does not exist, what does that imply about other things? That's what we'll look at.
Okay.
Or if it's not easily computable. Sometimes we have to just rely on a graph.
Oh, Lord.
Yeah. Find the limit as x approaches 1 of g of x where this is true. So I got this weird piecewise function where g of x is equal to x plus 1 if x is not 1. And pi, weird, pi if x equals 1. Okay? Now, does direct substitution work here? Like if I truly wanted to plug in g of 1, what is g of 1? What is g of 1? Pi. So is the limit pi? No. So what I truly have to do is say, well, what's the left side limit? The limit as x goes to 1 from the negative, well, going from 1 to the negative, or 1 in the negative direction, it's going to lead me to this guy, right? Anything to the left of 1 is going to give me x plus 1. So that would be 2. Right? So the limit from the left is 2. And likewise, using that same logic, going from the right is also going to get me this, which is also 2. So I can see that the limit from the left is 2, and the limit from the right is 2. And as long as they match, as long as the limits match, then the full limit as x goes to 1 of, what do we call it? G of x, then is 2. Okay? So if you can think about the limit from the left side separately than how you think of the limit from the right side, it might be easier. Okay? That's another case where, again, direct substitution didn't work there because it was a piecewise. And piecewise are a little weird. For piecewise, usually you're kind of removing something and calling it something different, like at a certain value. So you got to think about more about what's happening around it rather than what's happening at it. Okay? Same type of thing here. Let's calculate the limit as h goes to 0 of 3 plus h squared minus 9 all over h. Can I do direct substitution as it says right there? No, because h going to 0 would mean that I would be plugging into 0 into the denominator, which is that's no good, no bueno. So maybe there's something that we could do around it. Is there something that's simplified? Let's FOIL the numerator. Okay, the limit as h goes to 0 of 3 plus h squared minus 9 over h is really going to be equivalent to, you're going to see a lot of times when I do things algebraically, I accidentally leave off this limit as h goes to 0 sometimes, and then I'll bring it back in the end, because that's just very cumbersome to write sometimes. So should it be there on every step? Yes. Will I forget to do it sometimes? Yes. Okay, so let's FOIL this. That's going to be 3 plus h squared is, right, which is 9 plus 3h plus 3h plus h squared. So 9 plus 6h plus h squared. Okay, so that's in the numerator, 9 plus 6h plus h squared minus 9 all over h. And now we see something very convenient, that the 9's cancel out. Why is that convenient? Well, that's convenient because now when I take the limit as h goes to 0 of 6h plus h squared, what can I do with my h? I can cancel it out everywhere, right? I can really, the way I should think about it is factoring out an h from the numerator, right? Making this look like this, h, 6 plus h over h. canceling it out. So we have the limit as h goes to 0 of 6 plus h. Now what is that limit? 6. So another case where we could reduce it down somehow. We just messed with it algebraically, basically, to see how it would reduce down. Okay, this next problem is going to be a little tricky. I would recommend writing down this problem because you're going to need to use this technique later on, especially in your assignment. I believe there's problems in your assignment that use this technique. We had this problem, section 2.2. We had this problem in the last section. And all we could do was run the numbers and plug and chug and say, oh, yeah, that's right. It comes out to 1/6. Right? So from our observations last section, we know that this comes out to be 1/6. But algebraically, why? Why does this come out to be 1/6? That's what we're going to look at right now. So we're going to find the limit as t goes to 0 of the square root of t squared plus 9 minus 3 all over t squared. And again, can I do direct substitution? No, I cannot. We're going to find that we're going to keep doing things that we cannot do direct substitution because if we could, the problem would be very easy. We just plug it in. All right, now, the issue is that we've got a denominator where it's just a singular variable in there. So what I'm going to do is actually bring something down into the denominator. I'm going to bring something down into the denominator. And I'm going to strategically pick what I'm going to bring down to the denominator. You know what I'm actually going to do? I'm going to actually unrationalize the denominator. Remember rationalizing the denominator? I'm going to kind of undo that. I'm going to bring that square root back down. And to do that, I take the conjugate of the numerator. No, it should be plus 3. The conjugate.
We should just simplify down the t squared plus 9, or no?
Say what?
Couldn't you just simplify down the t squared plus 9, or no? Like, just do the square root of it?
No, you can't do that.
Why not?
That doesn't work like that. Algebraically, that doesn't work like that.
Oh.
This is not true. T squared plus 9 isn't like t plus 3. It doesn't work like that. You would have to have something like this. It would have to be like the square root of, put a not equal to there, like t plus 9 squared. That could reduce like that.
Okay.
And then you could just make it t plus 9.
All right.
Right?
Yeah.
So you can't do that.
Why are we doing plus 3?
Let me show you why. Because now remember that this is kind of like two big chunks right here, right? I'm going to FOIL this all. This is actually going to turn out to be a difference of squares.
Yeah.
That's why the minus and the plus. Okay, so take a look here. I'm going to do my firsts. I've got the square root of t squared plus 9 times the square root of t squared plus 9. Well, if I multiply square root and square root, doesn't the square root go away? So that's going to end up being t squared plus 9. That's our first. The reason why I do the plus 3 is to make the outers and the inners cancel. Look, this would get me a 3 square root t squared plus 9 and a negative 3 square root t squared plus 9. So they will cancel and I won't even have to write it. That's why. And then at the end here, look, negative 3 times positive 3, it just so happens, ooh, that's nice. Now on the bottom, I just have to go straight away here. T squared, and then square root of t squared plus 9 plus 3. And what's really nice is the plus 9 minus 9 will cancel. So I'm going to get t squared. Oh, that's a t. That's a t squared. T squared over t squared, quantity square root t squared plus 9 plus 3. And now my t squares will cancel out of the denominator. And now I won't have the problem, okay. Now I won't have the problem of the denominator equaling 0. This is going to be a 1 over t squared plus 9 inside the square root plus 3. And look, I did because I'm lazy, I forgot to write the limit as t goes to 0 of all of those things in the top step. Now can I plug in 0? Yes. Now I can plug in 0. Now I can say 1 over the square root of 0 plus 9 plus 3, which the square root of 9 is 3, plus 3 is 6. That's how it's 1/6. So if you have like a square root in the numerator, there is a technique where you can bring it back down to the denominator, unrationalizing the denominator, putting the square root back into the denominator, because technically all I'm going to do in the end is plug something into it anyway. So it's not going to be like unsimplified in the end. I'm going to plug something back into it, so it's okay to bring a square root back down to the denominator. It's okay to do that. Okay. Let's do one more example. Any questions on this one before we move on? Okay, let's do one more. Some limits are best calculated by first finding the left-hand and right-hand limits. I kind of did that earlier by looking at the left side limit and the right side limit. The following theorem is a reminder of what we discovered in section 2.2. It says that if the limit as x approaches a from the left as L, and the limit as x approaches a from the right is L, then it's the full limit is also L. Okay? So for example here, when show that the limit as x approaches 0 of the square root of x is equal to 0. Okay. Now, could I do direct substitution here? Yes, but it's saying show that. Show it. Okay, we're going to show it by using one-sided limits. Remember that the square root of x is really like a piecewise function, right? It's saying, okay, what's that? Get that out of there. There we go. The absolute value of x is just equal to itself if x is positive or equal to 0. And the opposite of itself if x is negative. I don't even really need to have the equal to 0. The equal to 0 does not matter because I am calculating the limit. So it doesn't matter where I put the equal to. Okay, well, let's calculate the sided limits, the one-sided limits. Let's calculate the limit as x approaches 0 from the low end, from the negative side of it. Well, if x approaches 0 from the left side, well, then it's the opposite, right? It's the opposite of it. But again, if x approaches 0 from the left side, it doesn't necessarily matter because it's going to look like negative x, right? And again, I keep forgetting to write. Get out of there. The limit as x goes to 0 from the left of negative x. Okay. But when I plug in 0, when I do the direct substitution, it'd be like negative 0, which is still 0. Okay. So let's run it from the other side. 0 from the positive. Well, that would be like saying, okay, the limit as x goes to 0 from the positive, the equivalent function would just be x, which is 0. Right? Why did I write it twice? I don't know. But I'm saying that the left side limit is 0, the right side limit is 0, so therefore the full limit, and the limit as x goes to 0 of the square root, or the absolute value of x is 0. Okay, this is kind of like almost like a proof, right? Showing by way of using one-sided limits that the left side limit matches the right side limit. Okay. While we're on this, I know we only have 6 more minutes, but I would love to do the next problem because it's got to do with this absolute value while we're in this mode of absolute value. Okay, let's do one more of these. Prove that the limit does not exist. Prove that the limit does not exist. How do you show a limit does not exist? You show a limit does not exist when the left side limit does not match the right side limit. Right? One way to show a limit does not exist is if the left side limit does not match the right side limit. Okay, so let's think back. The absolute value of x is really x if x is greater than or equal to 0, and negative x if x is less than 0, right? Okay, so let's calculate the one-sided limit. Let's say, okay, if x goes from the negative of the square root of x over x, well then, it would be here. So what is the limit if I'm coming from the negative? -1. Right? Well, let's calculate it going from the right then. The limit as x goes to 0 from the positive. Okay. Well, that would be the absolute value of x over x. Well, if it's positive direction, it's just going to be x, which would reduce down to 1. Right? And remember, why is it not 0? Why is it not 0? Because this ends up being a constant. Like truly what I should have really written was this. The limit as x goes to 0 from the negative of -1 is -1. And the limit, let's turn that into an L, of x going from the positive direction of 1 is 1. Well, what did I just show? I just showed that the limit from the left side is -1, and the limit from the right side is +1. Therefore, the limit going to 0 of the absolute value of x over x does not exist. Because the left side limit does not match right side limit. Okay? So if you're ever asked to prove that a limit does not exist, try to see what's happening on the left side and the right side of it. Because if what's happening on the left side and the right side are different, then then you can show that the limit does not exist. It's one of the only ways that we can actually algebraically prove that the limit does not exist. If the left side does not equal right side. Okay? Try to remember that every time you work with an absolute value, split it up into this piecewise thing. Because more often than not, that's going to help you along the way. Yeah?
How did you pull that piecewise from the absolute value of x? Because if it was like negative x inside the absolute value, wouldn't that turn into a positive?
Well, say you can turn it into a piecewise because now we're defining what values of x go to what thing.
Mm-hmm.
Like, so if I say, okay, if x is -1, it uses this rule, right? So -1 turns to +1,
mm-hmm.
which is technically the absolute value of x. The absolute value of -1 turns +1.
Yeah.
You know what I mean? So the absolute value of x is defined by this piecewise function where if it's positive, it's just the same number. If it's negative, then it's the opposite of that number.
Oh,
Does that make sense?
Yeah.
So I'm not really changing it at all. I'm just defining it a little bit more precisely so that we can find the limit of it easier.
Yeah.
Okay. All right. Sorry. I wanted to try to get that example in so that we didn't have to come back and do that tomorrow. All right.